Well, with this video, the course takes a little bit of a shift. We've done a lot of work with trig functions, the basics of the unit circle, how to graph trig functions and shift them, translate them, and everything else. We've done applications with right triangles. And now we're going to take a little bit of a break and work on trig identities. There's a lot of different equations in trigonometry that relate sines and cosines and tangents and sine squares and secants and all that together. We're going to both work with individual formulas, and then we're also going to prove things. So, I mean, not two-column proofs like you did in high school geometry, but here we are verifying trig identities. The stuff in this section is a little bit on the simpler side. The stuff as we move through only gets more complicated because the formulas get more complicated. And for the sections after 5.1, you will get a formula sheet on the exam, so that'll help you to not have to memorize everything, although there are some formulas in trig like sine squared plus cosine squared equals 1 that you really should know because you use them so often. So if you look through the PowerPoint, the beginning is me just sort of introducing what it is that we're doing. Right? How do you know if relationships between trig functions are valid? And some people like this stuff because they say it's like a little puzzle. There's more than one way to do a lot of these problems, and when you solve them, you're not really solving them for a variable. You're showing that both sides of the equation mean the same thing. And so you get to pick different formulas to use in order to accomplish that. Now, like I mentioned, there are a number of trig identities that you'll know off the top of your head. Others you'll reference that formula sheet for, and I'll show you that when we get to the next section. So some of the basic trig identities that you're going to know. For example, sine squared plus cosine squared equals 1. What if I said I want to prove this? Well, you could take a graphing calculator or something like Desmos and graph two equations. You could graph sine squared plus cosine squared, and you could graph 1, and you could show that they're the same thing, right? One function lies directly on top of another. So that is one way of verifying them. We're going to verify things algebraically by doing what? Well, you're going to end up with two things that are equal, and your goal is to work down one side of the equal sign and show that it matches the other side. You can actually work down both sides and get them to match each other. We generally don't try to cross that equal sign unless we absolutely have to, if there's nothing else that you can think of. I mean, if you're running a test question or something like that and you can't figure out any other way to do it, then yeah, you can cross the equal sign. I'm sure the textbook does it a couple of times too, but generally we try not to cross that equal sign unless we've run out of options. So how do you do these problems? And it'll make more sense after you see a couple of them, but this is a list that's in the PowerPoint, so as you go through the first couple of homework assignments, you might want to look at this list, and if you can't think of anything else, try one of these options. So one of them is turning everything into sines and cosines, and that's something that works not only for this individual section, but you'll see that in courses beyond Precalc, right? There's a lot of calculus problems that can be solved by turning things into sines and cosines, and it makes it easier, even possible, to solve the problem. Another one is factoring, right? Factor out common factors and simplify. Sometimes combining terms into a single fraction will work. Sometimes, if nothing else works, multiplying both sides of an equation by a binomial factor, right, a sine squared plus cosine squared, or sine theta minus cosine theta, something like that. Oftentimes, we can do that top and bottom of a fraction on the same side of the equal sign, and when we can do that, we will. So, some basic things that you're going to need to know to do these problems. First one are the reciprocal identities, right? Secant is the reciprocal of cosine, cosecant is the reciprocal of sine. Tangent and cotangent are reciprocals of each other, and if you notice, I wrote tan as sine over cosine, and a reminder that when you flip them, cotan is cosine over sine. All right, the Pythagorean identities we did in the last chapter, sine squared plus cosine squared equals 1, and then the two that you get from dividing through. So if you divide through by sine squared, that gives you the bottom one, the 1 plus cotan squared, and if you divide through by cosine squared, that gives you the 1 plus tan squared. And of course, any version of that will work too. So for example, I've got sine squared plus cosine squared equals 1, but it's also true then that 1 minus cosine squared x equals sine squared x. So I may have to take one of those equations and move them around a little bit in order to come up with something that will help me to verify the identity. So here, let's start with the first couple. First one says tan theta cosine theta equals sine theta. Well, I see sines and cosines and I see a tangent, so maybe I'll try turning that tangent into a sine over cosine. So here I've got sine theta over cosine theta times cosine theta. And notice I can get rid of the cosine theta, and I end up with a sine theta on this side. Now, carry down the equal sign. You notice now I have equals sine theta. Is it really that easy? Yes, the first one really is that easy. I end up with sine theta on the left. I end up with sine theta on the right. The two are equal to each other. Done. All right, for number 2, when I see a 1 plus sign and a 1 minus sign, I'm thinking maybe let's multiply this out. So 1 times 1 is 1. Notice this is a difference of squares pattern. So 1 minus sine x and sine x times 1 go away. And then I'm left with the product of the insides, which cancels out the 1 minus sign. And now when I do the last, sine x times negative sine x is negative sine squared x. So I get 1 minus sine squared x. Well, okay. Remember about 30 seconds ago I had said that if sine squared plus cosine squared equals 1, then if I subtract the sine squared x from both sides, then I get cosine squared x equals 1 minus sine squared x. So I can replace that 1 minus sine squared x with a cosine squared x. And again, now if I carry down the equal sign, I get cosine squared equals cosine squared. Right? Were there other ways to do it? Yeah, there's other ways to do it too. And like I said, if you had gotten desperate, you could flip things over. And the other thing too is I could have taken that cosine squared, and I could have taken the cosine squared and turned it into a 1 minus sine squared, and then factored the 1 minus sine squared and made the left and right side equal each other. So more than one way to do that one too. All right, look at number 3. I got a 1 over cosine squared and a 1 over cotan squared. Well, maybe there's a nicer way to write these reciprocal functions. So 1 over cosine squared is secant squared. And 1 over cotan squared, that's the reciprocal of cotan, which is tan. Now, if you go back to my identities, one of the identities was 1 plus cotan squared equals cosecant squared. And the other one was 1 plus tan squared equals secant squared. Oh, that's the one I'm looking for, right? This one here that involves tan squares and secant squares, but it doesn't look like the equation that I have here. Because here I have secant squared minus tan squared. Well, if you look at that line over there, subtract the tan squared from both sides, and sure enough, I have the same thing, right? So secant squared minus tan squared equals 1. So secant squared minus tan squared is 1. So yes, 1 equals 1, and it's verified. All right, let's take a look at number 4. For number 4, I've got a sine cosine over 1 minus cosine squared, and on the other side I have a cotan. So how do I approach this one? Well, I know an identity for 1 minus cosine squared. Didn't we just do it on the other page? And again, if you forget which way it goes, if sine squared plus cosine squared equals 1, if you subtract a cosine squared from both sides, then you get sine squared. All right, so I can replace that 1 minus cosine squared with a sine squared. And that gives me sine x cosine x over sine squared x. And now, you notice I'm multiplying these together. You can't do it if you're adding, but you can do it if you're multiplying. So break them apart. Make it sine x over sine x times cosine x over sine x. And you notice when you multiply across the top, you're back to a sine x cosine x. When you multiply across the bottom, you've got sine x times sine x, which is sine squared x. So you haven't changed the fraction. All you've done is you've rewritten it in a different way. But now sine x over sine x is just 1. Look what you've got. You got cosine over sine, which is cotan x. So cotan x equals, and notice I never touched the right-hand side of this equation, and I never went across that equal sign. I worked entirely on the left-hand side to get it there. I could have taken cotan on the right and turned it into cosine over sine and made them equal to each other at that point. That would have worked as well. All right, number 5. A couple of options for number 5. There is a temptation to cross that equal sign and just get rid of that sine squared from both sides and do the same thing with the 1, but let's try to avoid that. So to do that, I'm going to work on simplifying this thing here first. Right? I got a sine squared over tan squared. So sine squared over tan squared is sine squared theta over sine squared theta over cosine squared theta, right? Sine over cosine is tangent. And then multiply by the reciprocal of that denominator. So multiply by the reciprocal of sine squared over cosine squared, so that I end up with multiplying by cosine squared over sine squared here, and then on the top, cosine squared over sine squared there. Right, so what does that give me? Let's line everything up correctly, because that sine squared is in the top, so here everything goes away. Done. On the top, I have a sine squared theta, really over 1, times cosine squared theta over sine squared theta. And look, the sine squared thetas go away, and I'm left with cosine squared theta. So that sine squared over tan squared is really just another way of saying cosine squared. Right? So I'm left with 1 minus cosine squared theta, and we've done this a couple of times. If you're in doubt, look up here. 1 minus cosine squared is sine squared. Right? So I get sine squared theta on this side, and all I have to do is bring down this sine squared theta on the other side equal to each other. Right? And so it's been verified. So I'm not solving anything. I'm not getting theta equals 3 pi over 4. I'm not getting sine theta equals square root of 3 over 2. I'm verifying that what's on the left side and what's on the right side are the same. Even though they may look very different from each other, they actually are equal to each other. Hey, this is kind of fun. Let's try some more. All right, take a look at number 6. Oh my goodness, that looks like a mess. But one thing I noticed that on the top, I've got a difference of squares. Even though they're fourth degree functions, it's really just a difference of squares. And here's what I mean. If you were to factor, let's say, x to the fourth minus y to the fourth, you'd factor it as x squared minus y squared times x squared plus y squared, right? If you multiply that back, you get an x to the fourth. Outside and inside will go away, minus y to the fourth. So I'm going to do the same thing here, except they're going to have sines and cosines. So I'm going to get sine squared theta minus cosine squared theta times sine squared theta plus cosine squared theta. And then on the bottom, I've still got my sine squared theta minus cosine squared theta. Okay, well now I got the same term top and bottom, so I can get rid of that top and bottom, and I'm left with sine squared theta plus cosine squared theta, which is 1. And now the 1 on the left side, the 1 on the right side are the same. All right, number 7 says, show in 2 different ways. All right, so one way is very easy. If you go back to the identities, I got a secant squared minus 1 and a cosecant squared minus 1. So if I subtract the 1 from both sides over here, secant squared minus 1 is tan squared. Over here, so secant squared minus 1 is tan squared. Cosecant squared minus 1 is cotan squared, right? Cosecant squared minus 1 is cotan squared. And now you realize that tan squared and cotan squared, if you multiply them together, you just get 1. Right? This one is sine over cosine. This is cosine over sine. And you just get 1. The other way to do this is perhaps a little bit more involved. You could multiply the whole thing out and then work with identities, right? So I'm going to erase what I have here because that was one of the ways to do it, right? Just turn them into tan squared and cotan squared, and I'll make a note up here. Tan squared theta, cotan squared theta is 1. All right, what's another way to do it? Another way to do it is you might look at that and say, all right, I'm going to FOIL the whole thing out. And I'll end up with secant squared theta cosecant squared theta minus secant squared theta minus cosecant squared theta plus 1. Ooh, wasn't that interesting? So what do? The first two terms both have secant squares in them. The third term has a cosecant squared. Maybe I can do something with that cosecant squared. So I've got here a negative cosecant squared plus 1. What can I do with a negative cosecant squared plus 1? Well, here, you notice that I got cosecant squared minus 1 equals cotan squared. So I got cosecant squared minus 1 equals cotan squared, which is kind of what I want, except not really, in that what I have here is a negative cosecant squared and a positive 1. Well, if cosecant squared minus 1 is cotan, that must mean that negative cosecant squared plus 1 is negative cotan. So it may happen every once in a while that what you're looking for is the exact opposite of what you have. So multiply through by a negative. So this thing here can replace a negative cotan squared theta. All right. Well, how does that help me? Let's take a look at these first two terms over here. These first two terms over here both have a secant squared in them. So if I pull out that secant squared, I'm left with a cosecant squared theta minus 1. Cosecant squared minus 1 is cotan squared. Right? So this thing over here is cotan squared. So I'm left with secant squared theta times cotan squared theta minus cotan squared theta. And look, they both have a cotan in them. So here I can factor out a cotan squared, and I'm going to get a secant squared theta minus 1 because I took my cotan squared out of the first group and I was left with a secant squared. Take a cotan squared out of a cotan squared and you get 1. Well, if 1 plus tan squared is secant squared, then secant squared minus 1 must be tan squared. So I'm left with a cotan squared theta times tan squared theta, and that's 1 because they're reciprocals of each other. And oh look, it matches the 1 on the other side. So part of my point in doing this was that when you do these types of problems, sometimes there's very easy ways to do it, and sometimes there's much more complicated ways to do it. And in a sense, we have a choice of whether we want to do it the easy way or the more complicated way. Both of them will work, but obviously one of them is easier to work with than the other. All right, I'm going to do the last couple of examples in another video because this one's getting a little bit long.